Welcome to Efiwe, excellence without stress.
Hello guys, it's your favorite chemistry tutor, Godson. Welcome to Efiwe, excellence without stress. Today we are going to be understanding a very interesting concept. But before we get into that concept, let's have this food for thought. Have you guys noticed that in chemistry, in the production of water, most times, 1 mole of hydrogen combines with half mole of oxygen to give 1 mole of water. 1 plus half equals 1. That doesn't make any sense mathematically. However, stoichiometrically, it does make a lot of sense. Join me on this journey as we get to understand this concept. Stoichiometry and mole concept is the topic we are considering. Now, having said this, we are going to be looking into this particular study in 4 different segments. We'll start with the introduction to the stoichiometrical concept or the mole concept. Then we get into the quantities of measurement in chemistry. From there, delve into the relationship between quantities. And finally, talk about stoichiometry of reaction. So let's get into it. What is stoichiometry? Stoichiometry generally describes the chemistry of amount. So which means to any layman that comes around and asks you, probably somebody that is not a science student or somebody on the streets just says, what is stoichiometry? It sounds like a very strange word. You simply describe it to the person as the chemistry that deals with amount. It's more like measuration in chemistry. So once you are quantifying things during a reaction or a process, basically what you're doing is stoichiometry. But let's give it a more profound definition. It is a branch of chemistry that deals with the application of the laws of conservation of matter and definite proportion. So which means the 2 laws that must be applied whenever you are dealing with stoichiometry is the law of conservation of matter and that of definite proportion. Looking into the laws, the law of conservation of matter, which is a very popular law, I presume every science student should know this law, states that matter can neither be created nor destroyed, but is converted from one form to another. The implication is that everything comes from something else, basically. For instance, let's say moi moi. Every single Nigerian should know what moi moi is. And you notice that moi moi is not plucked from a tree. The first thing that happens is that you get your beans, and then your beans is eventually ground. You add your ingredients, it's boiled, and then it turns into moi moi. My point is this: it went through different stages of changes. They had to be changing from the beans to the moi moi. The beans was not destroyed. It was simply converted from a particular form to a better form, which is sweet and delicious. Let's continue. Another illustration to explain this is probably your wooden seat that you are sitting on while watching this video. It used to be a tree before, and now it's a seat. It's a chair. It's something you used to relax, or something you are sitting on to watch this video. The tree was not destroyed. The tree was simply converted from a particular form to another, and that is the whole concept behind the law of conservation of matter. So with respect to reactions, just note that in some cases a reaction, a particular thing might have or be in a particular form, but after a while it tends to turn into another form. That is basically what the law is trying to say. The next law we need to understand in our understanding of stoichiometry is what we refer to as the law of definite proportion. Another name for this law is the law of constant composition. So let's get to it. It states that all pure samples of a chemical compound contains the same number of elements which are combined in the same simple proportion by mass. What exactly does this mean? So let me just go back and get my board. Take this out so that we can be able to see my board. Okay. So already I wrote this down. If we consider this particular setup, I presume everybody in their different houses should have water in their house. That's why I'm using water. I could use any other thing, but we're going to be using water. Every single student, whether an Efiwe student or a non-Efiwe student, when you are considering the molecular formula of water, it contains 2 elements. The 2 elements that are highlighted in this case are hydrogen and oxygen. if you consider water in another person's house, it is also hydrogen and oxygen, same elements. But that doesn't stop there. The elements that are combined must be combined in the same proportion before you say that it is a compound. So what is the proportion of combination in water? 2:1 in an Efiwe student's house, 2:1 in any other student's house. So the point is this, that once you are dealing with the law of definite proportion, every time you are considering a pure compound, it must contain the same elements, and those elements it contains must be combined in the same proportion. Let's say, for instance, another person tells you that they have H2O2 in their house. Please, is this water? No. Why is it not water? It contains the same elements, but then it does not have the same proportion, which means this is definitely not water. So have that in mind, that when you consider the law of conservation of matter and the law of definite proportion, these two laws, when applied, would actually help us understand the concept of stoichiometry. Let's say, for instance, you have silver combining with chlorine to give AgCl. If, for instance, you have that 108 grams combines with 35.5 grams, what is likely the mass that you're supposed to have here? According to the law of conservation of matter, all the masses that are on this other side will actually be converted to produce this particular guy. So when we have 108 plus 35.5, it should be able to give us 143.5. I presume this is quite understood. This will bring us to the end of our understanding to the introductory parts of stoichiometry. Hello guys, welcome to Efiwe, Excellence Without Stress. This particular section of the study is going to be majorly discussing the quantities of measurement in chemistry. So let's get into it. There are about 4 major quantities of measurement in chemistry, and we'll be discussing each of them, defining them, and talking about their units. The very first one is amount in mole. To define a mole of a substance, it is described as the amount of that substance that contains as many elemental entities as that contained in 12 grams of carbon-12 isotope. The implication of this statement is that the particular quantifier or determinant of a mole of a substance is 12 grams of carbon-12 isotope. So once a particular substance has the same number of particles, the same number of atoms, or the same number of molecules as that found in 12 grams of carbon-12 isotope, automatically that is what we describe as a mole of a substance. The reason for the creation of the concept of mole is because reactions occur in molecular level, and the particles, when they react, are quite small or infinitesimal. Hence, scientists will not be able to pick up molecules and react them together. So they had to find out a particular quantity that is reasonable to react with. A very good way to understand this is if I had asked you, how many cubes of Maggi or how many seasoning cubes are you going to use to cook a grain of rice? It does not make sense to compare a cube of Maggi to a grain of rice. But when I now say a cup, you now have a quantity that makes sense. So that's basically the concept behind a mole. And as I said, the quantifier or the major determinant of that quantity is 12 grams of carbon-12 isotope. Moving ahead, a mole is basically measured or has the SI unit of mole. So once you see a particular question and they say 0.5 mol, not mole per dm cube, not molarity, once you see mol, or in some cases mols, what you are describing at that point is a mole of a substance. So moving ahead to the next one, mass. A mass is simply described as the quantity of matter contained in a body. In chemistry, mass is usually measured in gram. Yes, we all know the SI unit of mass is kilogram. However, in discussing chemistry or chemical quantities, we usually measure mass in gram. Major reason is this: the quantities we deal with in chemistry are usually small, infinitesimal, at least for our basic secondary school chemistry. So because of that, measuring in kg would actually not be very comfortable. Hence, in chemistry, we usually measure mass in gram. To the next one. The mass of 1 mole of a substance is what we refer to as the molar mass of the substance, and it is numerically equivalent to the relative molecular mass. So just have that in mind, that if you are asked to find the molar mass is equivalent numerically. I did not say they are the same thing, but numerically they're equivalent. Let's look at the board to help us understand exactly what I mean. Okay, so let's bring our board back. So if we consider a particular situation, let's say for instance, you have that the relative molecular mass of NaOH is equals 40. The implication is that if I ask you for the molar mass would be equivalent to it. But this time around, it is going to have a unit. The unit of molar mass is gram per mole. So just have that in mind, that if the relative molecular mass of a substance is something, the molar mass is simply that same thing numerically, but then it has a unit. And what is the unit we are dealing with here? Gram per mole. So let's continue. Now, so I have mentioned that whenever you are dealing with molar mass, the unit of molar mass is simply expressed as gram per mole. Moving ahead, the next quantity of measurement we are going to talk about is volume. So what is volume? Volume simply describes the space occupied by a substance. So any space you are occupying now simply describes your volume. In chemistry, the units majorly used include liter, centiliter, dm cube, cm cube, and the rest of them. You have meter cube too, and as many as possible that could exist. But the point is this, that the ones we are going to be concentrating with respect to our studies would be cm cube and dm cube. The liter and centiliter is usually the American curriculum that uses that. So if you see liter, centiliter, in most cases it is most likely an American question. So let's continue. The volume of 1 mole of a gas at STP. When I say STP, I mean standard temperature and pressure. We'll get to see what that means in our consequent videos. So, but just note that the volume of 1 mole of a gas at STP is known as its molar volume. So anytime you are asked what is the molar volume simply describes the volume of 1 mole of a gas at STP. And it has a constant value of 22.4 dm cube per mole, or 22,400 cm cube per mole. And finally, we will talk about the last quantity of measurement in chemistry, and that is number of particles. Particles are constituting components of a substance. So those parts that make up a substance are referred to as the particles. And in chemistry, there are 3 major particles of matter, which include atoms, molecules, and ions. These things are going to be discussed in other videos. So let's move ahead. The number of particles contained in 1 mole of a substance is known as Avogadro's number, and it is equivalent to 6.02 times 10 raised to power 23. So do take note of all these values have been given, because when we get into calculations, I am going to be making reference to each of these values. Having said this, the final thing about the quantity of measurement in chemistry, before we get into other parts, is that when you are asked to find the number of atoms instead of the number of molecules, the number of atoms is equals the number of molecules multiplied by what we refer to as atomicity. So anytime you are given a question and you are asked what is the number of atoms and you have the number of molecules, you simply do the number of molecules multiplied by its atomicity and you get your number of atoms. For us to understand what I just explained, I think you should know what atomicity is. So let's explain that. Atomicity simply describes, or is simply defined as, the number of atoms inside a molecule. Some molecules have 1 atom, some others have 2, some have 3. In fact, fullerene, which is a crystalline allotrope of carbon, has up to 60 carbon atoms inside 1 molecule. So you just have that in mind, not to talk of polymers that probably have up to 1,500, some large proteins and the rest of them. But the point is this, that once you are looking at the number of atoms in a molecule, that is what describes its atomicity. With that said, we will look into some trends that occur with respect to atomicity in different elements. Now, for every element that is a gas, except noble gases and ozone, it is supposed to exist as a diatomic molecule. So anytime you notice that it is a gas, you should have 2 atoms in one molecule. Let's put that down in our board so I will be able to understand this clearly. Okay, where is my board again? Where is my board? Okay, so right here. So let's look at that. So if, for instance, let's take this out. If you are to consider, let's say, for instance, you are dealing with, there are 11 gases in the periodic table, and out of the 11 of them, 6 of them are noble and 5 of them are your normal gases. So basically, if you consider hydrogen, because it is not a noble gas, I am going to have 2 atoms of hydrogen inside one molecule. If I'm to write fluorine, I'm not going to write fluorine like this because it is a gas. Once it is a gas, automatically it should have 2 atoms. So in every symbol, the symbols basically describes 4 parts, or 4 pieces of information are given in a symbol. You have that the atomicity is written at this point as a subscript towards the right. On this other side, you have the charge. On this other side, you have the atomic mass or mass number, and then here you have the atomic number. So just have that in mind, that anytime you are dealing with a particular symbol, these are the informations you are likely going to get from this particular symbol. So hence, our atomicity guy written as a subscript towards the right will be represented here. I take it again. Once it is a gas, there are 2 atoms in one molecule of every gaseous element, not just every gas, but every gaseous element, with the exception of your noble gases and ozone. So nitrogen 2 would also have N2. That's exactly why we write oxygen as O2. Moving ahead. So the next trend of atomicity we are going to be considering is the fact that noble gases, metals, and most solid non-metals exist as monoatomic molecules. So once you are considering a noble gas, a metal, and most solid non-metals, you represent them as monoatomic. Let's see what we mean. The implication of that statement is that you are going to just write 1 atom. If you are asked to write or represent a particular noble gas or a particular metal, you just need to just put down 1 atom, and that is the representation. For instance, if you are asked to write helium, helium is going to be written as just He. No 2 is monatomic. If you are asked to represent sodium, Na, monoatomic. If you are asked to represent calcium, if you are asked to represent carbon, which is a solid non-metal, sulfur is usually represented as monoatomic. However, in some cases, you would notice that rhombic sulfur, which is the crystalline allotrope of sulfur, can be represented as S8. So it just depends. In most cases, your solid non-metals are supposed to be monoatomic, but you could have exceptions like phosphorus. Phosphorus is P4. However, most of the solid non-metals are represented as monoatomic molecules. Having said this, we'll get to the final part of the trends of atomicity in a particular element. And what is that trend? The trend is that halogens are represented as diatomic molecules. Anytime you're considering a halogen is represented as a diatomic molecule, which means you have 2 atoms inside one molecule of every halogen. And what are the halogens? Your halogens are your group 7 elements, which are basically the elements whose spelling ends with INE. Basically, I just noticed it anyway. So your chlorine, your fluorine, your bromine, your iodine, and the rest of them. Basically, those guys are your halogens. Okay, with that said, we are going to now consider how to find molar mass using the atomic masses. And as I said, whenever you are asked to find the molar mass, it is simply the sum of relative atomic masses in 1 mole of that substance. Let's consider this. Find the molar masses of the following. You have H2SO4, which is sulfuric acid, your ammonium carbonate, your potassium heptaoxodichromate 6, and 1 mole of chlorine gas. So these are the things we are going to be considering to find their different molar masses. Okay, so let's go back to our board. Get that up and take the slide out. Yes, so we can solve. So So with that said, let's take all these things out. Okay, very good. So we'll start with the first one. The first person we are considering, or the first compound we are considering, is H2SO4. Remember that to find the molar mass, you just add the individual atomic masses. So the first thing we should do is to outline the individual atomic masses. Hydrogen has the atomic mass of 1. Sulfur has the atomic mass of 32. Oxygen has the atomic mass of 16. So let's add everything together basically. So we are going to add hydrogen. How many hydrogen atoms do I have here? I have 2. So hydrogen times 2 plus sulfur, just 1, plus oxygen times 4. So now let's put in their atomic masses and get our answer. So hydrogen has the atomic mass of 1. So that's going to be 1 times 2 plus S is sulfur, which is 32, plus 32. Oxygen is 16. So that's going to be 16 times 4. If you add all this together, you're going to have 2 plus 32 plus 16 times 4 is 64. So that should be, that's 98. So you have 98. If this was relative molecular mass, there will be no unit. But because this is molar mass, the unit is going to be gram per mole. So our answer for H2SO4 is that the molar mass of H2SO4 is going to be equals 98 gram per mole. And that's that basically. We'll solve one more question, then you guys are going to do the rest. The next one we're going to solve is ammonium carbonate. So solving for ammonium carbonate is quite simple. First of all, let's put down the formula down so we'll see it. Ammonium carbonate is NH4, you have 2, then we have CO3. Now, the atomic masses is important, you know them. Nitrogen is equals 14, hydrogen is equals 1, carbon is equals 12, and oxygen is equals 16. Discussing this atomic mass is actually done on another video. So please do make sure you are following our studies to be able to access these things. Now, nitrogen would have to be added to hydrogen, carbon, and the rest of them. So let's put all these things together. So to find the molar mass of ammonium carbonate, NH4 bracket 2 CO3. Please mind you, this particular 2 outside is multiplying everything inside, so do not be mistaken. So let's get to it. So nitrogen, how many nitrogen do we have? We have 2 nitrogen atoms in the whole mole, plus how many hydrogen atoms do we have? We have 4 times 2 hydrogen atoms, so that's going to be hydrogen times 4 times 2 plus 1 carbon atom plus oxygen multiplied by 3. With all this said, let's put in their values. So you have 14 multiplied by 2 plus 1 multiplied by 4 by 2. That's going to be 8 plus carbon, which is 12, and then 16 times 3. So if we do this, this is going to be 28 plus 8 plus 12 plus 48. If we had to add all this together, this is supposed to be 20, 48. Yeah, 48 plus 28 is going to be 68 plus 8, which is going to be 76. So our answer is going to be equals 76 gram per mole. So that is that about the molar mass of ammonium carbonate. So having said this, the final thing we are going to be discussing in this particular section of the video is molar concentration. Why do we need to know this about molar concentration? It's not necessarily a major quantity of measurement, but it is usually used in relation to these quantities of measurement. So what then is molar concentration? Molar concentration simply describes the number of moles found in 1 dm cube of a particular solvent. So anytime you are dealing with a molar concentration, you are looking at the amount in moles contained in 1 dm cube of that particular solvent. So as you can see on the screen, let's have that. Yes, so a molar concentration is the amount of a substance dissolved in 1 dm cube of a substance. The unit of molar concentration is mole per dm cube. However, in some questions, you might not see it as mole per dm cube. You might see it as molarity. The other way it is usually expressed is simply by writing capital M. So if you don't see mole per dm cube, you see molarity. If you don't see molarity, you are going to see the capital letter of M. These three things simply describe the molar concentration. Now, mathematically, molar concentration is expressed as C equals N over V in dm cube, where C is the molar concentration, N is the number of moles, and then V is the volume in dm cube. If you rearrange that, you are going to have that N is equals C times V in dm cube. This has brought us to the end of this section of the video. Remember to do your tests on the app, and also if you don't have this particular app, make sure you download it. Thank you very much. Welcome guys to Efiwe, Excellence Without Stress. And in this section of the study of stoichiometry, we are going to be discussing the relationship between the different quantities of measurement mentioned earlier on. Now, the reason this is important is, as we all know, you go to the market to get rice. There are different quantities that are used to measure rice. You have your cup, you have your Congo, you have your derica, your bag, and so many other quantities depending on where you are. But the point is that there is always a relationship between cup and Congo. Take for instance, it is possible that most likely there are about 10 cups in one Congo of rice. In a bag of rice, there are presumably about 200 cups. So you are able to relate these things such that when someone says, I give you one bag of rice, you understand how many cups of rice the person actually gave you. That's where this particular study comes in. When I say 1 gram of a substance, can I actually relate it to mole? If I say 2 cm cube of a substance, can I actually relate it to mass? And let's get into that. Now, the study, as I said, is going to be relating every quantity that we discussed to each other. Starting with the first one. The first relation we are going to be discussing is the mole to mass relation. Now, that is to say, we are relating number of moles to mass. And how is it related? By a straightforward formula. Number of moles is equals mass over molar mass. I take it again. Once you are asked to relate mass to number of moles, it is simply expressed or given by the formula. Number of moles is equals mass over molar mass. We're going to take questions to understand this later, but let's run it through. Then the second one is, how do I relate mole to volume? If you are going to be relating number of moles to volume, it is going to be expressed by the simple formula of number of moles is equals volume in dm cube divided by 22.4 dm cube per mole, or number of moles equals volume in cm cube all over 22,400 cm cube per mole. Now, some of you are already complaining and murmuring, there are too many formulas to learn. The thing about this is, when you practice with these things over and over with our test questions, which is going to be found in the app, you would notice that you become used to them and it becomes easier for you to retain. So don't bother about cramming them. As we solve as many questions as possible in the tests part of the app, you will find out that these things will be in your head. So let's move ahead. So the next one is the mole to number of particle relation. How do we relate number of moles to number of particles or number of molecules? It is simply expressed as number of moles is equals number of molecules divided by 6.02 times 10 raised to the power 23. Now, please do not forget that in our earlier video, we said that if you are specifically asked to find the number of atoms, after getting your number of molecules, what you are supposed to do is that you are supposed to multiply this number of molecules by the atomicity, and then you get your exact number of atoms. As I said, we're going to practice questions to help us understand this thing. We go to the fourth relation. The fourth relation is the relationship between mole and concentration, and that is expressed as concentration equals number of moles over volume in dm cube, or number of moles is equals concentration multiplied by volume in dm cube. Now, in some cases, you might have that your volume will not be given in dm cube. Instead, it will be given in cm cube. There is a very simple way to resolve that. So let me take this out so we can see it. Now, if for instance you are given a question and instead of giving you the volume in dm cube, it was given in cm cube. It's very simple. Note that volume in dm cube is simply related to volume in cm cube by v in cm cube divided by 1000. So anytime you are given a particular volume in dm cube, or you are given a particular volume in cm cube and asked to find its equivalent in dm cube, divide by 1000, which means v in cm cube is going to be equals volume in dm cube multiplied by 1000. Now, with this understanding, if you have a formula n is equals c times v in dm cube, and you find out that you do not have your volume in dm cube but in cm cube, just replace this v in dm cube with cm cube over 1000, and it becomes n equals c multiplied by volume in cm cube divided by 1000, and you have your answer there. Now, the other thing you could do is to convert your volume in cm cube by dividing it by 1000, then you get your dm cube value and then impute it into the formula, and you still have your answer. So whichever way you decide to use, just note that the major relationship between volume in dm cube and volume in cm cube is expressed thus: volume in dm cube is equals volume in cm cube divided by 1000. Having said this, we'd have to go back to our slide. So I presume you should be able to see it right about now. Okay, so we said that the relationship between the number of moles and concentration is going to be concentration is equals number of moles divided by volume in dm cube, or you have number of moles equals concentration times volume in dm cube. We go to the next one, which is the mass to volume relation. The mass to volume relation is simply equating the mole to volume and the mass to volume formulas together, and you have your answer. So the implication is that the mass to volume relation is equals mass over molar mass equals volume in cm cube over 22,400 cm cube per mole. But when your answer or your question is now given such that the volume is in dm cube, it will now be given as mass over molar mass equals volume in dm cube divided by 22.4 dm cube per mole. As I said, we're going to be practicing a myriad of questions, and as you practice those questions, these things will tend to stay in our head. So if you've not gotten the app, do get the app now. So let's continue, because these questions, yes, a lot of these questions, or all the questions you need for you to be able to understand this concept, will actually be found in our app, the Efiwe app. So let's continue. The mass of the particle, anyway, can be related to the number of particles using the relation mass over molar mass equals number of particles all over 6.02 times 10 raised to power 23. So let's just put that down so we'll see exactly how it should be on the screen. So having said that, the mass to number of particle relation will now be given as mass over molar mass equals number of molecules or particles divided by 6.02 times 10 raised to power 23. So once you are asked to relate mass to number of molecules or particles, this is what you're supposed to use. Now mind you, I've mentioned this before and I'm saying this again, that the number of atoms is expressed as number of molecules multiplied by atomicity. So if you have a question where instead of asking you for number of molecules, they ask you for number of atoms, after you have found the number of molecules, you now impute it into the formula number of atoms equals number of molecules multiplied by atomicity. So once you have that, automatically you get your number of atoms. So you have that. So however, remember I am emphasizing this particular formula for mass to number of molecules. So once you are relating the mass to number of molecules, please not number of moles. Moles and molecules are not the same thing. A mole is a quantity, a molecule is a particle. This is one of the things we've discussed in our earlier videos. Now, having said this, we would go back to the slide. Where is my slide? Okay, having said this, we will talk about the next relation, which is the mass to molar concentration relationship. The direct formula to relate this thing is mass over molar mass equals concentration in mole per dm cube multiplied by the volume in dm cube. If, for instance, you had a scenario where the volume is now in cm cube, instead of writing volume in dm cube, you will now have volume in cm cube over 1000. Or, better still, convert your cm cube value to dm cube and then impute it into the formula. So, do well to memorize these formulas by solving as many questions as possible. Then we go to the final relation for this particular study, volume to number of particles. So relating volume to number of particles would imply that it will be expressed by the formula volume in cm cube divided by 22,400 cm cube per mole, which is the molar volume, equals number of particles divided by 6.02 times 10 raised to power 23, or the volume in dm cube all over 22.4 dm cube per mole would be equals number of molecules divided by 6.02 times 10 raised to power 23. So then, once we are solving questions, all you need to do is this. Look out for what you are asked to find in the question and what you are given. Relate the two of them by their formulas, and then you have your answer. Let's try some questions. We are asked to calculate the mass of chlorine gas, which occupies a volume of 1.12 dm cube at STP. I take it again. The question says, calculate the mass of chlorine gas. Remember, we are asked to find mass, but then we are given volume, which means amongst our relation, we are given, or we have a mass to volume relation. A mass to volume relation, which is number 5. Now, let's check out the options. If you look at the options, you will notice that the mass is measured in gram, but then the question has the volume in dm cube. So, in the mass to volume relation, are we going to use the one that has cm cube or the one that has dm cube? Obviously, the one that has dm cube, because in our question, we are given the volume in dm cube. Hence, the formula to solve this question will now be mass over molar mass equals volume in dm cube all over 22.4 dm cube per mole. Okay, so let's go to our board. Let's leave this particular. So, to solve this question, we are going to write out the given parameters. And what were we given? The volume of chlorine was given in dm cube, and that volume in dm cube is equivalent to 1.12 dm cube. Now, with this, the next thing that we were actually given or asked to find is the mass of that chlorine gas, which has this value. Remember, in this case, you are given the volume in dm cube and asked to find the mass. The formula we are going to use, as we have discussed, is mass over molar mass equals volume in dm cube divided by 22.4. So just have that in mind, that this is basically what we are going to be using. Now, to solve this question, we will need to have the molar mass. So let's get the molar mass first. Molar mass of chlorine. Chlorine is a diatomic molecule, so it's Cl2. And when you are given molar mass, you are asked to add all the atomic masses. The atomic mass of chlorine, as given in the question, is 35.5. So, which means we are going to have 35.5. But then there are two 35.5, so multiplied by 2, which is going to be equals 71 gram per mole. So you have that as the molar mass, 71 gram per mole. We've gotten that. So let's put these things into this particular formula and get our answer. The mass is what we are looking for. The molar mass that is given is 71 gram per mole. Remember, we are looking for the mass in gram. And then, on the other end, the volume that was given in the question is 1.12 dm cube, all divided by the constant molar volume, which is 22.4 dm cube. Now, if we are to cross multiply and make mass the subject of formula, you find out that the mass is going to be equals 71 multiplied by 1.12 dm cube, all divided by 22.4. So if we are to divide this is likely going to give us 3.55 grams. So 3.55 grams is going to be our answer. So let's check our options. to see if it is there. My slide, where are you? So let's get back to the questions. Where exactly are you going to? Okay, so we have the question right there on the screen right about now. Okay, so we're able to solve this, and then we have the options. What option is likely correct here? And that is option C. We have 3.55 grams. So that's basically how to relate it. Let's try one more question that will help us understand this. How many moles of oxygen would be contained in 1.204 times 10 to the power 24 molecules? So you are given the number of molecules and you are asked to find the number of moles. Let's go back and see which of these relations should suit this particular process. So if you look at it, number of moles to number of particles is given as number of moles equals number of molecules divided by 6.02 times 10 to the power 23. So very easy to solve. The first thing we need to do is to take our slide away and then get to our board. Okay, so this is the question. This is the question we are asked to solve. Yeah, so let's get to that. So as stated earlier on, the formula we are going to be using is number of moles equals number of molecules divided by 6.02 times 10 raised to the power 23. Now, remember we are asked to find the number of moles. We don't know that, but we are given the number of molecules. And that number of molecules is 1.204 times 10 raised to the power 24. Dividing this by 6.02 times 10 raised to the power 23, you find out that the number of moles would now be given as 2 moles. You can use your calculator or you just use your head. Basically, you are going to get 2 moles. So you have that this is the answer. Now let's look at our options to see if that is actually part of the options. So putting up our slide again so that everybody can see. What option is that? That's option B, and that is the correct answer. I presume this has been helpful in your understanding of relating the different quantities of measurement. Welcome guys to Efiwe, Excellence Without Stress, and we are going to be studying the final part of stoichiometry, which is the stoichiometry of reaction. Now, this particular aspect of study has a lot in common with cooking. Why did I say this? When you are making a meal, cooking of meals is basically understanding the right proportion of things to combine. Yeah, I guess Hilda Bassi should agree to this. But yes, that's what it is. Once you combine the right proportion of things together, your meal will come out very wonderful. That implies that if you combine excessive seasoning cubes with a little quantity of rice, now you sabi how you go to chop that one. But let's continue with what we are saying. The point about it is this, that it has to do with proportion. So that same way, in combining chemical substances, you have to always consider proportion. There's a particular quantity of hydrogen that should combine with a particular quantity of oxygen to give a particular quantity of water. And once you're able to understand this proportion, you can actually determine what mass you should react with what mass to give what mass. You get what I'm saying, basically. So let's get into it. The rules that we are going to be considering when we are dealing with our understanding of stoichiometry of reactions include the following. So we'll start with the first one. The very first rule is that we should write a balanced equation for the reaction. So anytime you are dealing with a stoichiometric process, number one thing you should do is to write an equation for that particular process. After you are done writing the balanced equation, the next thing you are going to likely do is to identify the expected substance. The expected substance is that particular substance you are asked to find in the question. So if I had a question, what is the number of moles of hydrogen that will react with 2 moles of oxygen? Remember that you are asked to find hydrogen, so that is your expected. However, the given substance is the substance with a given numerical value. And what was that in the question I asked initially? oxygen. So once you have a value attached to something, that's the given substance. Then once you're asked to find something, that's the expected. Okay, now remember, these rules only apply when a reaction is occurring between two elements. It's not the rule for conversion of quantities. It's the rule that applies when a particular substance reacts with another. Then number 4, relate the expected to given as direct proportions in relation to the balanced equation, which is quite simple to understand. So just consider what happens in the balanced equation and then relate it to what the question says, and boom, your answer comes out. Now, for you to be able to understand this perfectly, the units on the same side of the relation must always be the same thing. So if on one side you have gram, and on the other side you have gram, mole, it's important you convert it. Okay, when we get to solve questions, you probably understand better. Now let's solve this question to understand these rules. Okay, so I'm going to have to reduce this so that we can be able to still see what we are doing. Just reduce this a little bit while we use our board. Sorry, I'm taking your time. Okay, I think it's reduced enough so that we can still see that and then also use our board too. Okay, so with that said, let's consider this. Now, if you look at the question says, how many grams of water is produced when 8 grams of hydrogen is reacting with excess oxygen? So the first thing we need to note is that water is the product. So we need to do the first rule, which is writing a balanced equation of the reaction. We can actually go back to that to look at the rules. So if you go back to the rules, you will notice that the very first thing you should do according to our rules is to write down a balanced equation for the reaction. So if you are doing that, that's the first thing. So let's move ahead anyway. So coming back to the question, you'll find out that to write the balanced equation of the reaction, I might have to take this whole thing out so that we'll have space to solve. So let's just take this whole thing out. Let's just take it out. I'll keep referencing to it basically. Now, having said that, to solve this is quite simple, as I said. So the first thing, write a balanced equation. Let's get to it. Hydrogen is actually reacting with oxygen. So we put that down. Hydrogen is reacting with oxygen because, as you saw in the question, they said water produced by 8 grams reacting with excess oxygen. So these are the two things that are reacting, and what is produced is water. Now, balancing it. Oxygen is 2 here, oxygen is 1. So we put 2 in front of the whole molecule so that it actually multiplies through. And then you now have 4 of hydrogen. So we put 2 here so that it becomes 4, 2. So this is basically the principle of balancing through. Now, having balanced this, the next thing we need to do is to identify the expected substance. Water is what they asked us to find. So we are going to put this as expected. Then we are now given the mass of hydrogen. The mass of hydrogen was given, so which means this is going to be the given. How do you solve this question? Very simple. Relate the given to expected. So from the balanced equation, 2 moles of hydrogen is equals 2 moles of water. Some of you might be wondering, how is it that this is 2 moles and not 2 grams? So just take note of it. Now, once you have a numerical value in front of a particular substance in a balanced equation, it is expressed in moles. So have that in mind. Okay, now that we have that 2 moles of hydrogen would give 2 moles of water, according to our question, 8 grams was what was given of hydrogen. We'll now produce how many grams of water? This is going to be very easy to solve. So should we cross multiply? Yes, that is what we should do. But then remember, we said something that make sure that the 2 units on the same side are the same thing. Here you have mole, here you have gram, so we can't cross multiply. Here you have mole, here you have gram, so we can't cross multiply. So what we need to do is to convert them such that they would be the same thing. So we can decide to convert this mole to gram or gram to mole. Whichever one is still okay. Just make your choice and do it correctly. So I think we should convert gram to mole for this side and maybe do mole to gram in this case. So let's do gram to mole so that we'll see how both of them, it works with both of them. So gram to mole in this case, remember that the relationship between mass and moles is N is equals mass over molar mass. Since we are converting the mass to N, we'll put it here and then have it to be 8 grams divided by the molar mass of hydrogen. An atomic mass, hydrogen's atomic mass is 1. 1 times 2 is going to give us 2. So this is going to be 2 grams per mole. And if we decide to cancel out, this is now going to be 4 moles. So instead of writing 8 grams in this case, it is expected that you are going to be putting down 4 moles instead. So we go to the other side. Now in this other side, we are going to be doing a conversion of mole to gram, majorly because our answer is in gram. So let's convert this to gram. So converting this is going to be quite simple. It's now going to be N is equals mass over molar mass. But because we want to convert the N to a mass, that means that this is going to be mass is equals N times molar mass. So mass is now going to be equals, number of moles is 2. Then the molar mass of water, this is going to be 1 times 2, which is 2 plus 16. And that is going to give us 18. So this is going to be 18 gram per mole. Now if you do that, you will find out that N is going to be equals, mass, the mass, not the N. We are converting to mass, is going to be equals 2 times 18, and that is going to be 36 gram. So the implication is that instead of writing 2 moles of water, what you are going to be replacing this guy with is with 36 gram. Now at this point, you notice that this is mole and this is mole, and this is gram and this is gram. Now you can cross multiply. So let's do the cross multiplication down here. This will now be 2 moles of hydrogen equals 36 gram of water. Therefore 4 moles of hydrogen will now give x gram of water. Cross multiplying directly, this is now going to be x times 2, which is 2x equals 4 times 36. Dividing both sides by 2, this is going to give you 2 times 36, and that is going to be 72 gram of water. So basically, let's see if that is even in the option. So let's go to our question basically. So if we put this up and open our slide, let me just expand it so it's more clear. Everybody can actually see it. Okay. I'm sorry, I'm trying to set it up. It's taking a little time, more time than expected, but I guess we are here, I think. Okay, so that's that basically. So you will notice that the option that coincides with our answer, which is correct, is 72 grams, and that's that basically. So once you are able to relate them properly, write a balanced equation and relate expected to given according to the balanced equation, your answer is definitely going to come up. Now let's try one more question to help us understand this basically. The second question we're going to be trying has to do with molar concentration, so please pay attention because it gets a little bit tricky here. Now the first thing I would like to say is, once you notice a volume associated with a molar concentration, like in this case they said 250 cm cube of 0.5 molarity, I mentioned that the units of concentration is mole per dm cube, molarity, or capital M. In this case they wrote capital M. So once you see capital M, mole per dm cube, or molarity, you are definitely talking about molar concentration. So once you have that volume attached to a molar concentration and it is stoichiometry, my first advice to you is to convert it to number of moles. So instead of writing this as a given, it is advised that you convert those two values to number of moles before you express them. So let's do that together. Let's take this out the board as usual. Okay, so taking this out and fading, let's come back to where is ours. Yeah, so we'll take everything out here and then come back to solving. Now as I said, the given was 250 cm cube of 0.5 molarity HCl. As I said, my advice is convert this to number of moles first. So the number of moles will now be concentration times volume. Because it's in cm cube, it means that we'll need to divide by 1000. But if it was in dm cube, we'll not need to divide by 1000. Hence, this is going to be 0.5 molarity multiplied by 250 divided by 1000. And when you do this, you are going to have 0.125 as your number of moles. So this is better to solve with than with these two, so it would avoid confusion. Now let's write our equation. Our equation for reaction was given and balanced Mg plus 2HCl reacting to give MgCl2 plus H2 gas. Okay, so with this now, we now write our values. We are asked to find the mass of magnesium. So this is the expected. And then we are given things with respect to HCl. So this is the given. So let's relate it. From the balanced equation, 1 mole of magnesium is reacting with 2 moles of HCl according to the equation. Then from the question, they now said what mass, so x gram of magnesium, will now be reacting with 250 cm cube of 0.5, but I said convert it to number of moles, and which we've done, and that is 0.125 moles of HCl. If we do this and cross multiply, our answer is going to be x. Now before we cross multiply, remember, you see that mistake I said we should try not to make. Before you cross multiply, ensure that the units on the same side are the same thing. This is mole, this is gram, so we can't cross multiply. But here, this is mole, so which means here is now okay, but here is not yet okay. So let's resolve it. Mole, gram. We are going to be converting mole to gram because our answer is in gram. Now, if you are converting mole to gram, it means that mass is equals number of moles times molar mass. According to the question, magnesium is 24. And the number of moles here is 1. So 1 times 24 would now give us 24 gram. Now, with this, M is equals 24 gram. The implication is that instead of writing 1 mole, what you expected to do is to put down 24 gram here. Gram, gram, mole, mole. Can I cross multiply? Yes. So cross multiplying, I'll now say 24 gram times 0.125. And that will be 24 multiplied by 0.125. moles would be equals x times 2. If you do this, the value of x will now be given as 24 times 0.125 divided by 2. This is going to be 12. So you have that 12 times 0.125 will now be given as 1.5 gram. Remember who we are looking for, mass of magnesium. And that's that basically on how to solve stoichiometry of reaction.
Having said this, we would now discuss some important things that are relevant to volumetric analysis. If you hear the term volumetric analysis, it involves an aqueous solution. So when you are reacting different substances in an aqueous solution, basically what you are trying to do or you're analyzing them is volumetric analysis. With that emphasized and said, there are important things that must be noted before we get into solving questions. The first thing that you should take note of is the term concentration. So whenever I say concentration, generally speaking, concentration is simply defined as the amount of solute divided by the amount of solvent. So generally, it's more or less the amount of solute found in a given amount of solvent. So when you are asked to mathematically express concentration, it is simply solute over solvent. Having established this particular fact, we move ahead to understand how it affects volumetric analysis. Now, there are two major forms of concentration that you must pay attention to whenever you are dealing with volumetric analysis. We'll start with the first one, molar concentration. So, when we say molar concentration, what do we actually mean? Molar concentration is simply described as the concentration of a substance in mole per dm cube. That is molar concentration, the concentration of a substance in mole per dm cube, which means mathematically molar concentration is expressed as number of moles of solute all over volume in dm cube of solvent. So just have that in mind, that when you talk about molar concentration, this is the general problem or equation for solving it. The SI unit of molar concentration, as I mentioned, is mole per dm cube. So in some cases, you will not see find the molar concentration. Some of the questions you will see find the concentration in mole per dm cube. When you see that, it's the same thing as molar concentration. Now, the unit for molar concentration is mole per dm cube, or molarity, or capital M. Any one of these three things are a representation of the molar concentration. Now, having established this fact, I would like us to also understand that molar concentration is represented by a symbol C, capital C. So once you see capital C, is actually a representation of molar concentration, which is measured in mole per dm cube. Okay, I think that's one of the most important things. Now, there are many ways to resolve or find the molar concentration of substances, and that is one thing I'm going to be establishing in this class. Let's look at the 4 different formulas that we should consider whenever we are asked to find molar concentration. There are more anyway, but let's look at these ones for now. The first formula you consider in finding molar concentration is when they ask you to find the molar concentration of a substance and your solute is in moles, represented by N, while your solvent is a volume in dm cube. So you simply use this to solve this, meaning that molar concentration will be number of moles divided by volume in dm cube. So if you have a question and they say 2 moles of a particular A is a solution containing 2 moles of HCl in 2 dm cube of water, what you simply do is 2 moles divided by 2 dm cube, and you have that your answer is going to be 1 mole per dm cube. So just have this, that this is the first formula for finding molar concentration. The second formula for finding molar concentration is C in mole per dm cube equals number of moles multiplied by 1000 all over volume in cm cube. This is actually a scenario where instead of giving you the volume in dm cube, your volume is now given in cm cube. And you have the third formula, which is also a formula for molar concentration, expressed as mass over molar mass times 1 over volume in dm cube. What does this mean? In a situation where you are not giving your amount in moles, but it's given in mass, what do you do to get the molar concentration? Mass over molar mass times 1 over volume in dm cube. And then finally, you have that molar concentration in mole per dm cube is equals mass over molar mass times 1000 all over volume in cm cube. So it's important, take note of these 4 major formulas because we are going to be applying them as we go further in this study. So when they say find the concentration in mole per dm cube, think of these 4 formulas. Anyone that suits it or coincides with the values you are giving is what you're supposed to use in that case. So just have that in mind. There are others, we're going to be taking them step by step. The second form of concentration that is important for you to note is mass concentration. Mass concentration. Now, it is related to molar concentration, but it is simply expressed as the concentration of a substance in gram per dm cube. So when you are asked for mass concentration, it simply means find the concentration in gram per dm cube. And what is it totally or mathematically expressed as? Mass of solute all over volume of solvent in dm cube. Now, if you don't use this, the other way to find the mass concentration is given as mass of solute times 1000 all over volume in cm cube. So it's important to take note of this, that mass conc is expressed as the mass conc is simply expressed as the concentration in gram per dm cube. So if they give you a mass and give you a volume, simply divide it and you get the mass conc. If you are given a mass and the volume is in cm cube, you need to do mass times 1000 all over volume in cm cube. As I said, we are going to be applying questions today, so don't be in a hurry. Now, having said this, the next important thing, I think it's very prevalent, we know, is how to relate mass concentration and molar concentration, because yes, there should be a relationship between the two of them. So what is the mathematical expression that directly relates these things? And that mathematical expression is simply given as mass concentration, which is measured in gram per dm cube, equals molar concentration, which is measured in mole per dm cube, multiplied by molar mass, which is measured in gram per mole. So have this in mind that anytime you are asked to find mass concentration, simply do molar concentration times molar mass. So in a case where you are not given the mass necessarily, and you have the molar mass of the substance and the molar conc, what do you simply do? Molar conc times molar mass to give us mass conc, which invariably, if we make molar conc subject of formula, it means that anytime we are now looking for the molar concentration, which is the concentration in mole per dm cube, what do we simply need to do? Making it subject of formula will now have mass concentration all over molar mass. Then finally, situations could occur or questions could come up. We'll see one of them here, where you will not be necessarily given the molar mass. That is, you will not be given the individual atomic masses or values generally to add and find the molar mass, which means that you should solve it using this formula. How would you now find the molar mass? Once you are asked to find the molar mass and you cannot find it by the conventional way, what you should simply do is mass concentration divided by molar concentration. Now, if you look at this thing, it actually makes sense. Just simply make it subject of formula. Anyone you make subject of formula actually gives us a new mathematical expression for our study. So take note of these things. We are going to be applying these things. That's why I'm actually talking about them before we get into questions. Okay, now having said this, I will now talk about one final formula, and we will now get into solving. Now, the final formula I'm going to talk about is the formula that relates molar concentration of reacting, and that's not reacting, of reacting substances in aqueous. So, oh, that's the wrong spelling of aqueous. Let's get that correctly. In aqueous solutions to their volumes. So once I'm relating the molar concentrations of reacting substances in aqueous solutions to their volumes, the mathematical expression used for that, how I pronounce it is quite funny, but then that's one way I used to remember it. It is referred to as, in my own terms, as kava na all over sebo vobo mbo. This doesn't make so much sense, but just have this in mind. It's simply CAVA equals NA all over CBVB equals NB. I'm just trying to put in that Nigerian vibe there. You know, the Kavana all over Sebo Vobo Mbo. This is basically one way to remember it. For those of you that might have issues with remembering this thing in the hall, this has helped me. It can also help you. So Kavana all over Sebo Vobo Mbo is just one way to express. And what are we establishing here? The relationship between the molar concentrations and their volumes. So have that in mind. Now, we are going to be understanding these parameters, because if you don't understand it and you apply, you are likely to have a doldrum of confusion when you are solving. I would like to start with the first guy here. When we see Ca, what does it mean? It simply means molar concentration of solution A. So when I'm asked to find the molar concentration of solution A, or maybe I'm relating it to solution B, the Ca here is simply representing the molar concentration of solution A, which is the concentration in mole per dm cube. Okay, then we have Cb. Cb is basically the molar concentration of solution B. Then we move ahead to the next thing, Va. Now, when we say Va with respect to this formula, Va is the reacting or titrated volume of A. It's not just any volume you see in the reaction, it's the one that is titrating. So when you look at a question, for instance, if you consider a question and they say put A into a burette and titrate it with, you heard titrate it with, so which means any value we get from the burette is our V of A. That is if A is added to the burette. You get what I'm saying? So have this in mind, that the titrated volume, not necessarily the volume of the solution, but the one that is titrated or reacting, is Va. Same way, Vb is also referred to as the reacting or titrated volume of B. So when you consider that, you have that. Then finally we have Na and Nb. Na is simply the number of moles of A in a balanced equation. So which means that before we get to find Na, we need to balance the equation, and any number of moles we get from there in a balanced equation is our Na, which means Nb is going to be the number of moles of B in a balanced equation. Okay, now why I'm literally explaining these things is they could be confusing terms. When you're asked to find the number of moles in a solution, you're not expected to use this. You get? So this is not the number of moles in a solution. This is simply the number of moles in a balanced equation. Okay, so that is that generally about this. Before I leave this and we get to solve a question, I would like to finally talk about dilution principle. Now, dilution principle simply has to do with a scenario where the solution basically changes concentration by adding more water. It's simple. The principle is given as C initial V initial equals C final V final. In my own term, on my own word, I just call it Psi Vi equals Sifo Vofo. Anyway, just have that in mind that this is the molar concentration initially times the initial volume equals the final concentration times the final volume. So once there is a change in concentration and you're expected to relate them, this is what to use. And in today's video, we're going to be considering an important concept, and that is the qualitative analysis. We'll get into it. In this particular study, whenever you talk about qualitative analysis, in describing qualitative analysis, you're looking at the constituents of substances. And for you to know the constituent of substances, there are certain things you should look out for. There are reagents that once they react, they will produce certain colors or maybe have certain effects. And once you see those things, automatically you understand that this is this substance. So what we're going to be doing in this study is we'll be considering certain tells. When I mean tells, I mean indicators. Once you see this particular thing, just know that it's this particular thing. You get? It's quite easy because, take for instance, you see a man walking towards you and that man is staggering. When he gets close to you, he has this smell of booze and alcohol. Nobody should tell you. You should automatically know that that guy is probably drunk. You get the point, okay? Or for instance, there's this tell I heard that when a girl likes you, that the girl begins to call you stupid names like idiot and stuff like that. Yeah, it doesn't make sense, but yes, that's a tell that they described as one of the indications for a girl that likes you. But that's not what we're here to discuss. What we're here to discuss are tells to indicate particular substances or constituent of compounds, basically. Okay, having said that, we're going to get into that. Now, I will just be talking or analyzing certain ions and discussing what is used for testing them, and then we'll use pictorial references to help us understand this. Okay, let's get into it. The first thing we are going to be considering are the tests for your cations. Now, the major cations that are going to be tested are lead, zinc, aluminium, iron 2, iron 3, copper, ammonium. These are the major ones we are going to be considering in this particular study. Having said this, we get into it. The two reagents that are used to test for cations are sodium hydroxide, an aqueous solution of sodium hydroxide, and ammonia. So the implication is that once you look at a particular question and you notice that they said add aqueous sodium hydroxide, it implies that you are likely testing for a cation. If you see add ammonia, it implies that you are likely testing for a cation. And what is a cation? A cation is a positively charged ion. It is a positively charged ion. So when you consider a cation, you're looking at an ion that has a positive charge, like Na plus, Pb2 plus, Al3 plus. These things are cations basically. Okay, let's get into it. So we're going to be considering how does NaOH affect cations and how does ammonia affect cations. Now, the general principle behind using sodium hydroxide is that when you use sodium hydroxide to react with salts, you produce the insoluble versions of those salts. Yes, because the only soluble hydroxides are sodium hydroxide and potassium hydroxide. Every other hydroxide of metal is insoluble. So when you react sodium hydroxide with any other salt of any other metal, it produces a precipitate. The precipitate means an insoluble salt. The color is what is going to help us understand, and its action when it is in drops and in excess will tell us exactly what we are looking out for. Now, with this thing said, there is one thing I would like to say, that in testing with NaOH, you first add in drops, and after adding in drops, you then add in excess. Now, if you add NaOH in drops, the first thing that happens is that the hydroxide of the corresponding metal will be formed, which will be indicated by the presence of the precipitate. And after that, you add NaOH in excess. Addition of NaOH in excess is to see if it will dissolve or remain. Now, the only substances that will dissolve in excess sodium hydroxide, the only substances that will dissolve in excess sodium hydroxide are amphoteric substances. Amphoteric substances. Amphoteric substances are substances that can react with both acids and base. And what are those amphoteric substances? You have lead, you have zinc, you have aluminium. These are the three amphoteric substances, which implies that once they are produced as precipitates in excess NaOH, they will dissolve. The implication is that every other precipitate does not dissolve. Why? They are not amphoteric. So have this in mind, that any hydroxide of lead, zinc, or aluminium will dissolve. Why will it dissolve? Because it is what? Amphoteric, and that is, it dissolves in excess. So you are seeing that with this now you have cleared some things. So whenever you see a particular reaction and you hear where the precipitate dissolves, you're either suspecting Pb, Zn, or aluminium. Every other precipitate does not dissolve in excess sodium hydroxide. Okay, let's get to work. Now, having said this, we're going to start with the very first one. I will consider the following metals. I would just like to put up just a picture that could help us understand this. Okay, so test for cations using sodium hydroxide. Now, the first thing is that anytime you introduce sodium hydroxide in drops to any salt that contains calcium ion, white chalky precipitates will be formed in drops. And after those chalky precipitate is formed in drops, if you add excess of NaOH, it will remain insoluble in excess. Remember, I told you that the only things that dissolve in excess NaOH are amphoteric substances. And what are the amphoteric substances? Pb salt, Pb hydroxide, aluminum hydroxide, or zinc hydroxide. Calcium hydroxide will definitely remain insoluble in excess. So have that in mind. Calcium will form white chalky precipitate, which remains insoluble in excess. And let me show you what I mean when I say a white chalky precipitate. Okay, so if we consider the image we can see on the screen now, if you look at this image now, you will notice that the precipitate is more like chalk dissolved inside water, and that is why it is referred to as chalky. The other thing about chalky is that chalky precipitates usually settle at the bottom after they are formed, as you can see on the image on the left. Basically, that particular precipitate settled at the bottom. That's actually the difference between the chalky and the gelatinous. And have this in mind, you could say chalky, you could also say powdery. These things represent the feature of calcium ion. The second ion we are going to be considering is lead-2 ion. Lead-2 ion, just like calcium, forms white chalky precipitates in drops. But the difference is that because it is amphoteric, it will dissolve in excess NaOH. So have that in mind. If you see a particular reaction and they said to this solution, add NaOH, and then you see that in the observation, I'm treating this like an alternative to practical. In the observation, you notice that you had a white chalky precipitate. Now, white chalky precipitate could indicate calcium 2 plus or could indicate lead 2 plus. How do we now differentiate it? If you add NaOH in excess, the white precipitate will not dissolve if it is calcium, but if it is lead, it will dissolve. Why? Because lead is amphoteric. Amphoteric means that it can react with both acids and base, which means it should dissolve in a base. So have that in mind, that Pb2 plus would dissolve in excess NaOH. However, when it is in drops, it just forms a white chalky precipitate. We go to the next one. I've indicated or shown you what I meant by the chalky precipitate. So we go to number 3. Number 3 is zinc 2 plus and aluminium 3. These two ions would form what we call white gelatinous precipitate. If you remember earlier on in this class, we said that zinc, aluminium, and lead are all amphoteric, which implies that they can dissolve in excess NaOH. So you have that. Now, zinc and aluminium will form white gelatinous precipitate, and those precipitates will dissolve in excess NaOH. So what do we mean when we say gelatinous? A gelatinous precipitate is more like, the term I like using is hanging precipitate. So if you notice this picture now, you'll notice that the precipitate is more or less hanging, unlike the one of that's the chalky precipitate. Let me bring that up. So if you notice the chalky precipitate more or less sinks to the ground or to the base of the beaker. But in the case of the gelatinous precipitate is hanging. So if you want to note or find out what you mean by gelatinous, just look out for the one that is hanging. So you find out that the picture we have here on the screen is the gelatinous precipitate. Why is it gelatinous? Because it is floating. More or less see it like that, that when you consider gelatinous, you're looking at the floating precipitate. Okay, so having said that, this on the right side is the chalky, this on the left side is the gelatinous. I just wanted to emphasize that just to help us understand this better. Okay, so moving ahead, that is what we refer to as the white gelatinous precipitate. So we continue our journey. Now, moving down to the next one, ion 2. Whenever it is ion 2 plus, think about dirty green. And that dirty green is a gelatinous precipitate, which means it is going to be floating or hanging in drops. But when you now put excess NaOH, it will still remain insoluble. I hope we know why. Because ion 2 is not amphoteric. It will not dissolve in excess NaOH. That's why. So you find out that for ion 2, you are considering a dirty green gelatinous precipitate. Okay, now if you look at the picture here, we have two test tubes. The one on the left side is ion 2, the one on the right side is ion 3. The one on the left side is dirty green. If you look at your picture or the picture very well, you notice that it is a dirty green, and that one on the left side is ion 2, while the one on the right side is reddish brown, and that is for ion 3. Both of them will remain insoluble in excess NaOH. So just have that in mind, that when you're considering the use of NaOH, when you put it in ion 2 salt, you have a dirty green gelatinous precipitate in drops, and that gelatinous precipitate will remain insoluble even in excess. In the case of ion 3, you have a reddish brown gelatinous precipitate in drops, which remains insoluble in excess. Then finally, we come to ammonium ion. Now, ammonium ion actually reacts with, every ammonium salt reacts with a base to form salt, water, and ammonia gas. So just have that in mind, that whenever ammonium ion or an ammonium salt, you introduce NaOH in an ammonium salt, you will not see any reaction, because you will have a reaction with NaOH to produce a soluble salt. So you will not notice the formation of the salt, because the sodium salt that will be formed is soluble. You will not see it. That's why in number 6 you saw shows no visible reaction. It doesn't mean that there's no reaction, it's just that you can't see it with your eye. Now, however, after you would not see that reaction, you would notice that a gas is going to be given off. One of the things that you are going to note is that as that gas is produced, it has a pungent smell. That gas is ammonia. So just have that in mind, that the gas referred to whenever ammonium salt reacts with NaOH, the gas that is produced is ammonia, and it has a pungent smell. Now, if you want to confirm that this is actually ammonia without any doubt, pass that gas through HCl, either the aqueous form or the gaseous HCl, and you find out that what you're going to have is a white dense fumes of ammonium chloride will be produced. So have that in mind, that if you want to test for ammonia gas, pass ammonia gas through HCl, and you have white dense fumes of ammonium chloride formed. So you have that. And these are basically the tests that once you consider, you will be able to indicate these ions. Okay, having said that, let's move on to the next one. The second reagent that is used to test for cations is ammonia. The second reagent that is used to test for cations is ammonia. And what do we have for ammonia? Now, in ammonia, you would have that in the case of sodium hydroxide, we were considering the amphoteric substances, and we said that once it is Pb, it is aluminium, or it is zinc, it will dissolve in excess sodium hydroxide. So you have that. Now, whenever you are dealing with lead, aluminium, or zinc, when the precipitate is formed, they dissolve in excess NaOH. Why? Because they are amphoteric. So every other metallic oxide or hydroxide that is precipitated during that particular reaction will not dissolve in excess NaOH, simply because those other ones are not amphoteric. These are the only ones that dissolve in excess. Now, in the case of ammonia, there are only two ions that will dissolve, or two precipitates that will dissolve, and that is Zn2 plus and copper 2 plus. This is simply because they form tetraamine complexes with ammonia, and those tetraamine complexes are soluble. So have that in mind, that the only ones that are soluble in ammonia are zinc and copper. So every other one will not be soluble in excess ammonia. So zinc and copper 2 plus dissolves in excess ammonia. What is the reason? Because they form soluble complexes with with ammonia. So just have that in mind, that initially when the precipitate is formed is as a result of production of the hydroxide, but when you now further add ammonia in excess, the only two ions that can form the soluble complexes with ammonia are zinc 2 plus and copper 2 plus. Okay, let's see what happens here. Now, if we consider these things, it's as if everything is practically the same thing. So Pb2 plus will form white chalky precipitate, and that precipitate will remain insoluble in excess. Now, however, when you consider the others, let's go to the next one. Aluminium forms white gelatinous precipitate in drops, which remains insoluble in excess. The simple reason is this, that aluminium does not form the tetraamine complexes. The only two substances that form tetraamine complexes are zinc and copper, and that is why they are the only ones that are soluble in excess ammonia. So just have that in mind. Okay, so if you are dealing with Pb2 plus, you have a white chalky precipitate which remains insoluble in excess. If you are dealing with aluminium 3 plus, you have white gelatinous precipitate, and that white gelatinous precipitate will remain insoluble in excess. Why? It does not form the complexes we talked about. In ammonia test, you are looking at the ability to form complexes. If it doesn't have that ability to form the amine complex, it cannot be dissolved in excess ammonia. Okay, so we'll move on to the next one. Zinc, on the other hand, has the ability to form the amine complex, so which means Zn2 plus, when it forms the white gelatinous precipitate, would dissolve in excess ammonia because it forms the zinc 2-tetraamine complex. Okay, copper would form a light blue gelatinous precipitate initially with ammonia. But when you now add excess of the ammonia, you are now going to have a deep blue solution formed. So I'm going to try to represent that. Okay, so we have two pictures here, as we can see. The one on the left is the first light blue gelatinous precipitate that is formed initially when you introduce ammonia solution in drops. But when you now add it in excess, you have the one on the right. The one on the right is the one that is formed, the deep blue solution that is formed in excess ammonia. So you have that. Initially, you will see something like this particular picture on the left. When you introduce aqueous ammonia in drops, this is light blue gelatinous precipitate. But when you now put the ammonia in excess, the copper 2 hydroxide that is formed now reacts with the excess ammonia to form a soluble blue copper 2 solution. So you have that. So that is the light blue on the left and the deep blue solution on the right. So have that in mind. So we go to the next one. Ion 2, ion 3 will just be the same thing as sodium hydroxide, which means ion 2 will form dirty green gelatinous, which remains insoluble. Ion 3 will also form reddish brown gelatinous, which remains insoluble in excess. So these things are our tests for our cations. Now, mind you, it is important for you to note that anytime you are testing with sodium hydroxide is not used for confirmatory tests. I take it again. Sodium hydroxide is not used for confirmatory tests. So, which means that anytime you are dealing with sodium hydroxide, you are not supposed to use the term confirmed. Use the term present, because sodium hydroxide is not used for confirmatory tests. In the case of ammonia, once you are done with your final test using ammonia, you can indicate that it is confirmed that this particular substance is there. Okay, so having said this, we are done with the major test for your cations. We'll now go to the test for your anions. Now, considering your anions, the anions I'm going to be considering majorly is dependent on the reagents we have and we are expecting in this exam. We have AgNO3. Now, acidified AgNO3, I prefer to use that term. Acidified AgNO3. Acidified AgNO3. This is silver nitrate salt. Now, acidified implies that you need to introduce an acid that's in drops in little quantity as you are adding the silver nitrate. The acidified solution implies that you are going to be adding a little bit of an acid. Any acid can serve, but preferably HNO3, as you are reacting the silver nitrate solution. So you have that. So is used to test for halide ions. So how does it work? Chlorine ion forms white precipitate. And please, I would advise that you don't do or try to abbreviate the term precipitate. This is the correct way of abbreviating. Small letter, all written in lowercase or small letter, and then you must introduce a full stop. But however, to avoid confusion, just use the normal spelling of precipitate. So chlorine ion forms white precipitate of silver chloride. That is, the white precipitate it forms is silver chloride. You get. Now, this silver chloride, which is the white precipitate of silver chloride, will remain, this white precipitate of silver chloride after formation will be dissolved in aqueous ammonia. Yes, wrong spelling of aqueous. Okay, so aqueous ammonia. So just have that in mind, that whenever you see AgNO3, just suspect halides. That is chlorine, bromine, or iodine. Just suspect these three things. When they say acidified AgNO3 or acid plus AgNO3, start suspecting a halide. If you see a white precipitate, automatically you will know that what is produced in that particular reaction is chlorine, or what is inside the solution is chlorine ion. Now, in the case where you see a milky precipitate, bromine ion would forms milky precipitate of AgBr. So you have that. So Br minus forms milky precipitate of AgBr, which dissolves in aqueous ammonia. So you have that both chlorine ion and bromine ion will dissolve in aqueous ammonia after their precipitates are formed. However, the final guy we are going to consider is iodine. Iodine ion forms yellow precipitate of silver iodide, which remains insoluble in aqueous ammonia. So please just have that in mind, that whenever you see silver nitrate, acidified silver nitrate, acid plus silver nitrate, and then they say add acid plus silver nitrate to the sample. Once you see white precipitate, you have that is chlorine. If you see milky precipitate, it is bromine. If you see yellow precipitate, it is iodine. Remember, chlorine and bromine are soluble in aqueous ammonia. And when you add the aqueous ammonia, you can now say chlorine is confirmed if it was white, and bromine is confirmed if it was milky. However, in the case of iodine, how do you confirm? When it forms a yellow precipitate and the precipitate which is yellow does not dissolve, what you simply say is that iodine is confirmed. Okay, we are going to try out questions to help us understand this more, but let's look out for more of the test. Okay, so the next test we are going to be considering is the test for glucose. Test for glucose. So what are we going to do about the test for glucose? It's quite simple. Now, first of all, before we get into the test for glucose, I would like to say this. Glucose is an alkanal. That is why it is referred to as an aldose sugar. And what do we mean by that? It has a terminal carbonyl group. If you consider the structure of glucose, 1, 2, 3, 4, 5, 6, okay, you have OH, H, OH, 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 H, 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 OH, H. Because it has a terminal carbonyl group, it means that this glucose is an aldose sugar. So just have that in mind. So this is the structure of glucose. And because it's an aldose sugar, it can be oxidized, which means once you introduce oxidizing agents to glucose, it is going to react. Now, we are going to just be considering different oxidizing agents that are likely used to test for this particular glucose. And what are they? What are the oxidizing agents that are used? The first one that is used is Fehling reagent. Fehling reagent. So on reacting with glucose, once you add Fehling reagent to a glucose solution and heat it, you are going to have a brick red coloration. Brick red coloration. Brick red coloration. The brick red coloration is an indication that the glucose has been oxidized while the Fehling reagent was reduced. You get what I'm saying? So Fehling reagent basically is a copper salt that is majorly constituting it. So copper 2 was reduced to copper 1. Copper 1 has a brick red color. So basically that. So that's that basically. If it was Fehling reagent and you're testing for glucose, you have a brick red coloration. Now, when you introduce the second one is Benedict's solution. Benedict's solution or Benedict's reagent. It would also give you a red color because still copper salt, even though they are different solutions. Red in some cases, or orange color. So once you add Benedict's and Fehling reagent to glucose, the color you are likely to have is brick red or just your normal red color. You get what I'm saying? So that's that basically. Now, the other oxidizing agents that can be used to test for glucose is your Fehling reagent. Fehling reagent. Now, Fehling reagent is basically a silver nitrate salt. You get acidified silver nitrate salt. And what happens in Fehling reagent is this: the silver will be reduced from a silver ion to a silver metal, and that silver metal will now paste on the surface of the test tube glass. So have this in mind, that when you introduce Fehling reagent to glucose, what happens is there will be a silver coating of the test tube walls. So have that in mind, that once you are dealing with Fehling reagent, if you introduce Fehling reagent to glucose, you have a silver coating, and that is a confirmatory test for glucose. Now, the other oxidizing agent that is used, even though this is not necessarily the best of confirmatory tests, is acidified potassium dichromate. That's heptaoxo dichromate 6. Once you do that, the color changes from orange to green. So have that in mind, that when you introduce glucose to Fehling reagent, brick red, Benedict solution, red or orange, Tolling's reagent, silver coating of the test tube walls, and then if it is acidified K2Cr2O7, which is your potassium dichromate, you have a color change from orange to green. And these are the tests for glucose. Now, the next test I am going to talk about is basically the test for a carbonate salt. The test for a carbonate salt is very simple and very basic. What is it? You simply add an acid, any acid. So add acid. Preferable acids to use are HNO3, dilute HNO3, H2SO4, or HCl. These are preferable acids to use, basically strong acids you get. So add acid to the solution. So once you add an acid to the solution, what are you going to see to indicate CO3? So CO3 2- is indicated by effervescence. So once you have effervescence, what I mean is, if you notice, if you open a Pepsi bottle or a Coke can and you have that sound, that foamy sound, and all those things, that is as a result of the high pressure because of the gases produced. That's what we refer to as the effervescence. So have that in mind. Now, once you have CO3 2- and you add an acid, you will notice effervescence. The first thing is, it will be indicated by effervescence to give colorless, odorless gas. So the gas that we produce would be colorless and odorless. So colorless and odorless. Now, if we want to confirm, because there are many colorless and odorless gases, hydrogen is colorless and odorless, oxygen is colorless and odorless, and so much more. But how do we confirm that it is from CO3? Now, it will produce a colorless, odorless gas. The gas we are dealing with is CO2. How do we confirm that it is CO2? When you pass it through lime water, the gas turns lime water milky. So the gas produced turns lime water milky. Okay, when I say lime water, I'm talking about calcium hydroxide solution. Okay, so you have that in mind. Now, what do we have here? We have that if I want to test for a carbonate salt, and what I'm used to test for a carbonate salt is an acid. Now, once you have sample plus acid, and you go to the observation, and you notice that in your observation you have a effervescence, which is followed by production of colorless, odorless gas. How do you know it's CO2? When they now say that it turns lime water milky, you now write in your inference, gas is CO2 from CO3 2-. So whether you are dealing with CO3 2- or the bicarbonate version, which is HCO3, they have the same test basically. So just have that in mind. Now, the next anion that I'm going to talk about is your SO4 2-, SO3 2-, and S2-. The reagent that is used to test these gases is, these anions I meant to say, is barium chloride. So barium chloride is used to indicate the presence of SO4 2-, SO3 2-, or S2-. Now, how does it work? Now, the very first thing you need to know is that barium forms insoluble salts with all of them, which means that they will all precipitate, and the salts they are going to form are white salts. So just have that in mind, because barium is not a transition metal. It's not a transition metal. So just have that in mind. So with that said, let's get to work. So in the test procedure, if BaCl solution is added to sample and white precipitate is formed, once you have that BaCl2 solution is added to a sample, once you see BaCl2, start suspecting SO4 2-, SO3 2-, and S2-. You know, in the earlier study or earlier on, I said once you see AgNO3, you start suspecting halogens. In this case, once you see barium chloride, start suspecting sulfate, sulfite, and sulfide. Sulfate is SO4 2-, sulfite is SO3 2-, and sulfide is S2-. So let's get to work. So if barium is added to the sample and white precipitate is formed, it means that SO4 2 minus, SO3 2 minus, or S2 minus is present. Now, please notice the terminology I use. I did not say SO4 2 minus, SO3 2 minus, and I said or, which means it's either of these three. So just have that in mind. Any one of these three can be the answer. Now, how do we find out or get a confirmation test for this? Now, to confirm, you add to confirm. That is to distinguish which of them is actually correct. So to confirm, add hydrochloric acid, HCl, aqueous. So if you add hydrochloric acid, SO3 2 minus and S2 minus will dissolve in HCl. So after adding BaCl and they say add HCl, once you notice that the precipitate dissolves, your answer becomes SO3 2 minus or S2 minus present, basically. Then dealing with the other one, SO4 2 minus, how would you confirm it? SO4 2 minus remains insoluble in HCl aqueous. So just have that in mind. And why it remains insoluble is because in our production of acids, if you look up that study, you will notice that there are three major ways to produce acids: direct combination, your direct combination, dissolution of your acid and hydrides in water, and then your double decomposition reaction. In the double decomposition reaction, a salt of a weaker acid can actually be dissolved in a stronger acid. But the other way around, it can work. That is to say, a salt of a stronger acid cannot be dissolved in a weaker acid. SO4 2 minus is a stronger acid than HCl. That's why its salt cannot be dissolved in HCl. Anyway, my point is this. Once you notice BaCl2, suspect 3 ions: SO4 2 minus, SO3 2 minus, or S2 minus. And how do we confirm that it is SO4 2 minus? If you add HCl and it remains insoluble, the white precipitate remains insoluble, automatically just know that it is SO4 2 minus. However, if it dissolves, you're suspecting SO3 2 minus or S2 minus. Now, before I end this and we get into a question, I just want to give basic tests for gases. So, test for gases. Test for gases. Okay, the first gas, as we know, is CO2. CO2 turns lime water milky. The next gas is hydrogen. Hydrogen has a characteristic pop sound. When you introduce hydrogen gas, introduce a lighter splint to hydrogen gas, H2 gives pop sound. When I mean pop, like the sound, just pop sound. So H2 gives pop sound with lighted splint. And when we say lighted splint is not so complicated. It's just like a wood, just a broken wood or a piece of wood that is on fire. You get what I'm saying? Once you introduce hydrogen gas, it extinguishes the lighted splint with a characteristic pop sound. And I said pop sound is like, I don't know if you heard that, but you know, that sound, that's the pop sound. Okay, then we go to the next one, which is oxygen. O2 gas rekindles glowing splint. It rekindles glowing splint. So what do I mean by that? A glowing splint is basically a wood that was on fire. However, after putting out the fire, that yellowish light that is still glowing, that's what we refer to as the glowing splint. If you introduce that glowing splint into a particular container with oxygen, the fire starts again. That's what we mean by rekindling. Now, there are two gases that rekindle glowing splints. Dinitrogen 1 oxide also rekindles glowing splint. So how do we differentiate the two? By their smell. This one has no odor. That is, it is odorless. This one has a sweet smell. So you have that. Oxygen gas is odorless, but dinitrogen 1 oxide has a sweet smell, basically. And you have that. Ammonia. How do we test for ammonia? Ammonia gas is tested using HCl. So it forms white dense fumes. fumes with HCl. It is also characterized by its choking smell to the pungent smell of ammonia. Okay, then we have H2S gas. Hydrogen sulfide gas is characterized by its rotten egg smell. So it has a rotten egg smell. So imagine a rotten egg. The smell of a rotten egg is actually the smell of H2S gas. However, the reagent that is used to test for H2S is a solution of lead-2 ethanoate. Why? H2S reacts with lead-2 ethanoate to form black precipitate. So forms black precipitate of PBS with lead-2 ethanoate.